Rodney Brooks developed the subsumption architecture in the 1980s in MIT. He claimed the approach of sensing, processing, then executing used in GOF-AI, good old-fashioned artificial intelligence, was a bad system for real-world robots to use. Also claiming that building world models and then using that information to plan and execute makes the response time too long and would even cause robotics researchers to focus on a bad strategy, seeing as the system can only be as fast as its slowest component. So in 1986 he offered his new solution based around a more reactive layered model instead of the old linear one. It was designed around breaking down the system into the different tasks of the robot's control system instead of internal workings like GOF-AI. This new way of approaching AI was difficult for the AI community to accept at first, and a lot of lobbying was needed to change the way AI is considered when constructed. He stated that his system was much more robust and flexible than the old one, with easier testing as well. The subsumption architecture is based on a number of layers, each implementing a behavior of the robot alongside the others in a hierarchy. Each layer has no idea what's going on in a layer above it, but can see the data of the layer below it, and even manipulate the input and output of the lower layer. Each layer is referred to as a level of competence, which informally specifies a desired class of behaviors. A higher competence level implies a more specific group of behaviors. This essentially means that more and more can be added to the specification of what the robot should do, with each layer being able to absorb the function of the layer below it, while adding its own functionality on top. When designing around a subsumption architecture, we should always start at the bottom with layer 0 and then build on top from there. Each layer is made up of a number of modules which are finite state machines, with input and output, which communicate with each other to implement a certain behavior. The input part is the data being sent in, and could be from sensors, output from other modules, and so on. Output is of course what the module produces from the input. This here is an inhibitor, which blocks the output for a given time when data is sent through the connecting wire, sending that data instead. Suppressors basically do the same for input, and reset just sets the module back to its original state. For the first layer, there could be the behavior of avoiding obstacles. There is a behavior language for this purpose, but to keep it simple, diagrams will be used for a simple method. This is the first layer of our system at competence level 0 for avoiding objects, each box being a module. The sonar module takes in the sensor data from, the sonar sensor, creates a map of obstacles to avoid using polar coordinates, and sends this to collide and free force. Now the system can figure out the level of danger of the robot coming into contact with something, with the field force treating the obstacles as repulsive forces and averaging these forces into a value. Runaway then commands the motor module if the force value gets too high. Finally, collide outright stops the robot if something is dead ahead via the motor module as well. Here we add another layer of competence by allowing the robot to wander around without hitting objects. The new wander module sets a new heading, which gets sent to the new avoid module. And this is where things get a bit interesting. At this point, the avoid module completely cuts off the runaway module as it's sending data. It does this as it takes the same field force value as runaway, but also uses it to modify the heading to roughly follow the path without hitting objects, and sends this instead of runaway, effectively absorbing or subsuming some of layer 1 to complete layer 2's objective. When layer 2 stops wandering for whatever reason, it effectively lets layer 1 run as normal without interference, meaning the system can still run at that level despite upper levels finishing requirements or just messing up. Also, when we want to add a higher competence level, we can add them to the top, provided of course we remember the order of the layers. Now the principles. There are a number of very strict principles made by Rodney Brooks when making design decisions for the robot, which are complex and useful behavior does not need to come from a complex system, make things simple, both with keeping an interface less complex than its components and with not solving ill-conditioned or unstable problems with the components or in the design. Make robots cheap while doing useful work around humans without their interaction, map making also being important. Three-dimensional world modeling is also important. Relational maps are more useful than complete coordinate systems. No artificial environments for the robot. Visual data gives a better description of the world than sonar being useful for lower level interaction. Built-in self-calibration must be working at all times for when sensor malfunction, and so recovery is quick. And finally, that robots are self-sustaining. Despite the initial criticism of the subsumption architecture, it had still taken off in the AI community and was used in various robots such as this one and this one. A great ethical concern when dealing with subsumption is the automation. Seeing as the core principles include working around humans without their intervention and being self-sustaining, the robot using this architecture may have no concern about its actions being dangerous or unethical if a specified risk was overlooked in the design. For instance, if the design does not account for blocking a door during a fire alarm while dealing with the recycling. Also, there may be concerns of bugs or poor design leading to danger. While the subsumption architecture helps to alleviate this with the layering of behaviors, an issue with pathfinding via poor sensors, for example, could lead to the robot running into people or damaging property, assuming this has not been planned for prior. Some say that in order to keep robots acting in an ethical manner, there needs to be an ethical framework used to constantly monitor the design and development of the system, keeping it safe. This framework also being coherent, applicable, and widely acceptable, while following a number of ethical principles.